Hello my dear students. In the last video in the last 3 videos in this series we have done some basics of what are vectors, what are scalars, how we can multiply vectors, how we can add vectors, right? So in this video we are going to talk about an important thing which is called differentiation. So we would like to know, given a vector field, how we can differentiate that vector field, right? So everybody is convinced that differentiation is an important phenomena, right? It's an important mathematical operator. It's actually a powerful operator we have. Why can you think of why differentiation is a powerful tool? Can you think of this thing? You can write in the comment box if you know, right, why differentiation is a powerful tool. Because you see, everything around us is changing. Everything around us is changing continuously, right? And rate of change is nothing but derivatives. In mathematics, when you try to model rates of change, then you have to seek the help of derivatives. So that is why differentiation is a very powerful tool which you are going to see in every field. Like you try to model anything from cars to finance, you will see the derivatives appearing everywhere, right? So differentiation for sure is a very powerful tool. So we would like to know how we can differentiate vectors. So it's very simple. I told you what is a vector field. So vector field is that, suppose we will keep it very simple. Suppose there is only one variable. So vector field means you have a function of u which is a vector. So you have something like xu I cap plus yu j cap plus zu k cap. Right? So how can I think of this thing, that it is kind of in place of just having generally when you have a function you have just x of u, that is a function, right? But now we have our function having three components: x component, y component and z component, right? Now we already know how we define derivatives for a function of one variable. Suppose I have this function. How do I define derivative? I define derivative as I will increase little bit in my function, the variable x, corresponding there will be a change in f, and then this is the change. This was f of x, this is f of x plus del x. Then you divide it with del x and you take limit del x going to 0. So whatever is this quantity, if it exists, because we know that sometimes limits, they don't exist, but if this limit exists, then we call it as the derivative of f, right? Okay, and physically they represent the tangents that we will discuss later. So here also you have a vector r which is dependent on u. So suppose this is my ru vector. So what I will do, I'll increase my parameter u to u plus del u. Suppose this is my r u plus del u, right? And then this vector here will be giving me r u plus del u minus ru. Okay, so this is that vector which is the difference. So what I am going to do, I'll take this limit del u going to 0, r u plus del u minus ru divided by del u, right? So what will be that? That will be x u plus del u I cap plus y u plus del u j cap plus z u plus del u k cap minus x u I cap plus y u j cap plus z u k cap divided by del u, and limit del u going to 0. So that would be, now you can separate, right? You can combine this term and this term because they both have I cap. So I have x u plus del u minus x u divided by del u, limit del u going to 0 with I cap. And similar thing I can do for the j cap terms, right? So I will be having limit del u going to 0 y u plus del u minus y of u divided by del u j cap. And the same thing I can do with the k terms, k cap terms. So that would be your, if I do this for the k cap terms, so that would be limit del u going to 0, z u plus del u minus z u divided by del u k cap. Right? Now, students, what is this? Can you tell me? Just forget about I cap. Just look at this quantity here. This x is a simple scalar function which we, have a very nice grip on. So this is nothing but rate of change of x with respect to u, I cap, plus rate of change of y with respect to u, j cap, plus rate of change of z with respect to u, k cap. So this is what your derivative of r with respect to t looks like. Fine. So for example, let us just take something, say you have a vector r is equal to say sine t I cap plus t square j cap plus 2t k cap. Then what will be my rate of change of r with respect to t? That would be dy by dt of sine t plus I cap plus dy by dt of t square j cap plus dy by dt of 2t k cap. So you are going to get, this is your cos t I cap plus 2t j cap plus 2k cap. So this is your dr by dt vector. So this is the answer you have here. So that is very simple, right? Now you know that we would like to, we are studying vectors because we actually want to work on the applications, right? So everything which we are studying in mathematics has this aim that you should be able to apply it in, applications somewhere. So one of the applications of derivatives of vector is finding the velocity and accelerations. So suppose you have a particle p, which is moving along a curve in space, right? So particles, we study particle motion, and suppose we have a curve in space. This is my x-axis, this is my y-axis, and this is my z-axis, right? And suppose this particle is moving in space along a curve, and we call it as a space curve, along a curve. Now, how do you define the curve? At any point of the curve, so you have the parameterization of curve. There is an x coordinate, which is a function of, say, time. Then there is a y coordinate, which is a function of time. And there is a z coordinate, which is again a function of time, right? Suppose time is the only variable we have here, right? So a particle is moving in space along a curve, which is given by the curve's equation is, you have, I just told you, you can think of it as a vector, xt I cap plus yt j cap plus zt k cap, right? So this is the position vector of the particle at time t, and we'll denote it with small r with a vector symbol on the top. Does that make sense? Okay, now if I ask you what is the velocity of this particle, we know that velocity is again a vector which is rate of change of the position vector. That is how we define velocity, because if I ask you what is the velocity, so you'll say that at whatever rate the particle is changing its position, that is my velocity. So that is nothing but rate of change of the position vector. So that would be rate of change of what is your position vector here, that is xt I cap plus yt j cap plus zt k cap, right? So that's going to be rate of change of x with respect to time I cap plus rate of change of y with respect to time j cap plus rate of change of z with respect to time k cap. So this is an interesting thing, that if we know the position vector of a particle which is moving along a curve in space, then we can for sure find the velocity vector for that particular particle. And then what about the acceleration? So for acceleration also, we know that what is acceleration? Acceleration is rate of change of velocity. So we know that this is rate of change of velocity vector. So if I ask you what is an acceleration, is it a scalar quantity or a vector quantity? So you know that this is a vector quantity. So that is given by dv by dt, where v is my velocity vector. So that is d2x by dt2 I cap plus d2y by dt2 j cap plus d2y by this last term should be involving z, d2z by dt2 k cap. So now you can see that very beautifully the results which we have in one dimensional or for scalar functions, they are being transformed to your vector valued functions. Can you see those things? Try to appreciate it. That's the beauty of mathematics, that you can build on, the same thing, you can generalize the concepts, right? Okay, so now let us do some problems. I'm giving you this question that suppose particle P moves along a curve whose parametric equations, and in this series we are preparing for, for a moment, we are preparing for IAS. This is vector analysis is a part of paper 1. Okay, paper 1. Otherwise also, if you are studying for any other subject like other exam, then also it's good, but for IAS specifically, this is paper 1. Okay, and this is one of the simplest topic which you can prepare, right? Okay, so for paper 2 we don't have it, but for paper 1 this is vector analysis, and it's very precise syllabus. We are going to cover it soon. Okay, so I was getting so many comments that we should be prepared, like making videos on vector calculus, because the stuff on vector calculus is limited, if you see, right? Okay, coming back to our question, suppose particle P moves along a curve whose parametric equation is x is equal to 40t square plus 8t, y equal to 2 cos of 3t, and z is equal to 2 sine of 3t, right? And the question is, determine its velocity and acceleration at any time t, And then we have another question, which is find the magnitude of velocity and acceleration. Find the magnitude of velocity and acceleration at t is equal to 0. Right? So let us do it, students. So we have here, if you look at this, so we have how shall I start with? First of all, I know that given the position vector, so I'll write my position vector RT. That is going to look like my x coordinate of the position vector times I cap plus my y coordinate of the position vector times j cap plus my z coordinate of the position vector times k cap. Right? Now, so that means dr by dt, that is my velocity vector, would look like the derivative of the first quantity 40t square plus 8t I cap plus the derivative of the second quantity 2 cos of 3t j cap plus the derivative of the third quantity k cap, right? So that is going to be 80t plus 8 I cap plus minus 2 sine of 3t j cap plus 2, it's a 3 also, right, here, plus 2 into 3 cos of 3t. I hope you know how we are differentiating. We are using the chain rule here, right? So my velocity vector looks like this. And what about my, okay, you can write it. So this is 80t plus 8i minus 6 sine of 3t j cap plus 6 cos of 3t k cap, right? So this is my velocity vector. Now I am looking for my acceleration vector. So if you are looking for your acceleration vector, so that is your rate of change of velocity with respect to time. I'm sorry, I'm writing double derivative, that is for r. Okay. So you just differentiate it once more. So you'll get 80 I cap minus 18 cos of 3t minus j cap right? And then you have minus 18 sine of 3t k cap. So this is the first thing, find the velocity and the acceleration part. Now find the magnitude of the velocity and acceleration at t is equal to 0. So how you are going to do that? You see that at t is equal to 0, I'll just put t is equal to 0 in my velocity vector. So if you put a 0 here, it's gone. So you'll get 8i, 0 here, it's gone, plus 6k cap. And then your acceleration vector at t equal to 0 is, this is 80i cap, and then you have, this is minus 18j cap, this is 0. So now I'm looking for the magnitude. You know that for magnitude we square the components and then we add and we take the square root, it's 10. And for acceleration also, if you take the magnitude, you 80 square plus minus 18 square, and that is 82. So we get these two are the speed. This is your speed, right? We know that the magnitude of velocity is called speed. So you understand how we can just do these problems, right? It's very interesting, right? In the next video, I'll do 2-3 more problems. Thank you for watching. Keep sharing this video and subscribe to this channel.